Good morning, everyone. Hope you're all well. It's Dr. Bennett here, and today we're going to be looking at cables. So we've seen recently, as we've learned more and more theory as the course has gone on, we've been able to go back and revisit some of the concepts that we studied earlier in the course. And basically revisit some of the assumptions that we made, and with the new theory that we've learned, go back and actually add in some more complexity to the problems to get a slightly more accurate answer. And that's what we're going to do today when we look at cables. So in the past, when we've looked at calculating tension in cables and ropes, for example, we've assumed that well, first of all, that the cables are straight, that the tension is equally distributed along the cable, and we've neglected the weight of the cable as well. So today we're going to revisit some of those assumptions and make some slightly more accurate predictions of tensions in cables. So first of all, let's consider this suspension bridge, right? So this is the main cable of the suspension bridge. The uniformly distributed weight of the bridge, this piece down here, is suspended or transmitted from the cable via these vertical lines. And we model this problem now as a distributed load. So we have the load due to the weight of this horizontal piece of the bridge being suspended by the main cable of the suspension bridge. And what we'd like to do is find out, for our analysis, to calculate the tension in this cable at any given point along it. So now we're assuming that the tension is not constant across the cable's length. First of all, we'd like to know the shape of the cable. So what's the function of this curve? Secondly, we'd like to find an equation for the tension in the cable so we can work out what that tension is at any point on the cable itself. And also we'd like to find out the length of this cable. So all of these three things are going to be interlinked with equations in a coordinate system which we define, so that we can find equations for the curve, equations for the length, and equations for the tension in the cable, and work out what's going on at any given point along it. So what we're going to do is formulate these three things separately. So there is a little bit of algebra here, so try to keep up. I'm going to deal with these 3 points in order, 1, 2, and 3. I'm going to formulate an equation for each of these three things. So first of all, let's take a look at the shape of the cable. So what we do is we cut the cable at the lowest point, right? So here. And we set that as the origin of our coordinate system. So we've defined a Cartesian coordinate system in the XY plane where the lowest point of the cable, which we've cut, is at the origin. And then what we have is a tension T acting in this direction at an angle theta to the horizontal, and we have a T0 acting horizontally at the lowest point. And then here I've drawn on a distributed load of magnitude W, which represents the weight of the bridge, right? So what I can do is apply the equilibrium equations to this. So if I sum forces in the X, I have a cosine component of T positive and a negative T0. in the y direction, I will have the sine component of t and subtract the magnitude of the distributed load, which basically is the area of this piece down here, which is x, if we assume this is the length x, multiplied by the weight w. So what I've tried to do to keep up with how I'm using these equations is just start to label them and then show you how I'm using them. So I've called these equations 1 and 2 respectively. So all I've done here is just rearranged 1 and 2 to get the sine and cosine components on the left hand side, and then these bits on the right hand side. And then I've called these two equations 3 and 4. So what happens is if I take equation 4, divide it by equation 3, I get sine over cos, which is tangent. The t's cancel, and then I just get wx over t0 on the right hand side. So what that does is gives me an equation which I can apply to this little triangle in here, where t gives me the hypotenuse, and then I'm calling the change in x and changing y dx and dy respectively. So what I can do is apply just a regular trigonometry to this triangle to say that the tangent of this angle is the change in y over the change in x, and then from there I've used this equation up here for tangent of theta to rearrange this equation in terms of wx and t0, multiplied through by dx to get this equation, and then because I'm integrating from the lowest point to the furthest point where t is acting, I can say that this distance here is x and this distance here is y, so I'm integrating between 0 and y on the left hand side and between 0 and x on the right hand side. So what happens is if I calculate those integrals, I get an equation for the shape of the cable. So intuitively it's a quadratic in x, right? We should recognize that shape, but I just have to include this term at the front, which includes the weight of the bridge, which we've modeled as a distributed load, and 2 times the tension at the lowest point, T0. And I've called that equation star to be used later on. So that's the equation for the shape of the cable. So that's number 1 dealt with. So now let's move on and look at how to calculate the tension in the cable. So up here I've gone back and used equations 3 and 4, which you'll recall were these two down here. So what happens is if I square both of those, I get the following. So all I've done is just squared each term on the left and right hand sides of both of those equations, and I've called those equations 5 and 6. So if I add these two things together, I get this, and then I can factorize the t squared out to get this, and you'll recognize with the identities, trigonometric identities, that sine squared theta plus cos squared theta is 1. So I get this. And I've just taken square roots of both sides to get an equation for the tension T. So this tells me that the tension in the cable is minimum at the lowest point of the cable, right? So where x equals 0. So when x equals 0, this term is 0, and I just get the square root of t0 squared, which is just t0, right? Which is what we said over here. So the tension at the lowest point when x equals 0 is t0, right? So that tells me that I've done my algebra correctly. It also tells me that tension is going to be maximum in the cable at the highest point, so for the highest value of X. Okay, so that's point number 2 dealt with. So I have now an equation for the tension in the cable. Now let's finally deal with the length of the cable. So a similar kind of technique here. I call an element of the cable ds, so that I can apply some trigonometry to say that ds is just the square root of the change in x squared over the plus the change in y squared. Factorize dx out to get this, and then I've used this star equation. So star equation, where was that? That was down here, look. The equation for the shape of the cable. So I've used that. So if y is equal to w over 2t0 times by x squared, then I can differentiate that like that, and then I can plug this equation into this equation. So I just replace dy by dx into here to get this equation. And then what I do to find the length of the cable S is just integrate this equation between 0 and x, and we end up with this lovely equation for S. Now this looks like a huge mess, and I wouldn't expect you to be able to integrate this to get this in an exam or whatever. It's not a calculus class. But if you were to be asked to find the length of a cable, then you will be given this equation on a formula sheet, for example. So that's our 3 equations for our 3 bits that we need to know about our cable: the shape, the tension, and the length. So let's now go ahead and have a look at a couple of examples. So here's the first example then. We've got this slightly anti-symmetrical cable supporting a distributed load of 100 pounds per foot. Height of the cable on the left hand side is 40 feet. Height of the cable on the right hand side is 20 feet, and it's 40 feet long. And we would like to find the tension in the cable at the lowest point. So as we've just discussed, I cut the cable at the lowest point and then set that as the origin of my coordinate system. So I've drawn on the information that I know from the question statement. Left hand side height's 40 feet, right hand side height 20 feet. This distance I've left off here, but the difference between x1 and x2 is 40 feet. So I don't know this length here, and I don't know this length here. So that's what I would like to calculate. I'd like to find the points x1 and x2. So the first thing that I can do is apply the equation that I found or derived previously for the shape of the cable. You'll remember it as this one. And I do that for both sides to find x1 and x2, right? So that's what I've done here. I've said y1 is the weight over 2t0 multiplied by x1 squared, and on the right hand side the same but with x2 squared. Remember, what I'm asked to find here is the tension at the lowest point, and that's what I'm calling T0, right? So ultimately these T0s should be the same, and that's what I'm trying to find ultimately. So recall this picture here where I described the tension at the lowest point as T0. So I've plugged in the information that I know. So the weight, the distributed load is 100 pounds per foot. The height on the left hand side 40, height on the right hand side 20. So then I've got two equations which I've labelled 1 and 2, which I can manipulate to try and find these coordinates x1 and x2. So the first thing I've done is taken number 1 and divided it by number 2. So 40 over 20 is 2 on the left hand side. These terms here cancel and I get just x1 squared over x2 squared. So that's another little equation that I can use, and I've called that number 3. And as we said before, this length here between x1 and x2 is 40 feet, so I also know this equation, which I've called number 4. So now I'm in a position to eliminate either x1 or x2 from this equation by using this equation and just rearranging it for either x1 or x2 and plugging it in. So I've decided to rearrange this one for x2 and then plug that in there. So I've said x2 is equal to x1 plus 40, and then replaced x2 in here to get this. And then if I rearrange that, I get this quadratic, which I can solve for x1. And now, so when I solve a quadratic, I get two roots of the equation, right? One positive and one negative. So obviously here, because of where I've set the origin of my coordinate system, I choose the negative root of that quadratic, right, which is minus 23.43 feet. And because I know that, I can put that into this equation, for example, to find what x2 is, and I should get a positive root, right, which I do, 16.57 feet. So once I know those coordinates, x1 and x2, it just becomes straightforward to find the value of t0 by using either of these two coordinates in either of these two equations. So I've chosen to use this one for y1. So 40 is equal to 100 over 2t0 multiplied by x1 squared, which I found over here. Rearrange that for t0 and I get 686.2 pounds. So a little bit of sort of equation manipulation, but really the only thing you needed to solve this equation was the equation for the shape of the cable. So that's example 1. So in the second example, we've got this suspension bridge. It's symmetric this time, so it's 36 meters long. The droop of the cable is 1.4 meters, and the bridge itself weighs 2,700 kilos. Two parts to this question. The first part is to calculate the maximum tension in the cable. So you'll recall the minimum tension of the cable, T0, is at the lowest point, but the maximum tension in the cable is at the highest point. So we need to work out what the tension is over here or there. The two things are equivalent, but we'll deal with this side because this will be our positive x-axis, right? And then the second part of the question is to find the length of the cable. So we know it spans 36 meters, but with this droop of 1.4 meters, what's the length of the cable? So the first part is we need to convert the weight of the bridge into a distributed load. So we're told that it's 2,700 kilos. So we find the magnitude of the weight by multiplying that by the acceleration due to gravity to get 26,460 newtons. And the bridge is 36 meters long, so we can work out per meter what that corresponds to. So we divide this by 36 meters to get 735 newtons per meter, and that gives us our distributed load. which I've drawn on my free body diagram here. So I've cut the cable again at halfway. I know it doesn't, my poor drawing here doesn't make it look symmetric, but it is. So it's 18 meters on either side. The droop is 1.4 meters, and I'm missing my coordinate system. So I've drawn on the distributed load, got all of the information, so I can go ahead now and apply the equation for the curve. So I've applied the same equation as I did in the previous example. Y is 1.4 meters, right? It's 1.4 meters when x equals 18 meters. I know the weight vector due to the distributed load, so I can plug all of that information in this equation and rearrange for t0, and I get this. So that gives me the tension at the lowest point, right? So I now need to use, now I know that, I now need to use the equation to find tension T, which you'll recall is this one. So this is the equation that gives me the tension T at any point x, so long as I know what T0 is, right? So this is the bit that I calculated just now. I know this, and so I can find the tension T at any position x. So in my example over here, to find the maximum tension in the cable, I need to find tension T when x equals 18 meters. So that's exactly what I've done, is I've used that equation and I've plugged in x equals 18. And I've found my tension as 86,072 newtons. So that's the first part. Second part, and by the way, so if I wanted to find the tension at any point along the cable, I'd use the same technique as I followed here, find T0 first and then use this equation, but then I replace x with whatever position that I'd like to find the tension T at. So in terms of this equation, T0 and W are both constants, and I just vary x to find T at any point. The second part of the question asked me to find the length of the cable due to the droop, right? So I have to go and use this lovely equation from over here, right, which we derived previously, and I just plug in x equals 18 meters. I know the weight, I know T0, so it just becomes an exercise in calculator bashing basically with this equation. And if I've spared you all of that writing, so I've basically plugged in these values which I found above to find that the length of the cable is 36.1 meters. So it's only 10 centimeters longer because of the 1.4 meter droop, right? So alright, so that's it for today. I'll speak to you all very soon. Cheers.